Okay, so I'm recording. Don't admit to any crimes. Don't incriminate yourself. Okay, sharing again, y'all can see.
Yep.
Perfect. Okay, thank you. Thank you very much. All right, so today's topic that we're going to be talking about. The first third of this course was essentially review from 121, like these are vectors, these are arrays, stack, queue, yada, yada, yada. The second third of the course was linked lists and trees. And now the last final chapter of the course is going to be more advanced structures. The main focus is going to be on the hash map and the graph. So for the next 2 weeks or so, we're going to be thinking about hash maps. PA5, I think, is released, so I would get an early start on that. Today, we're going to be going over like the conceptual, what you need to know about hashing, and hopefully that should prepare you a little bit for PA5. And I think I will be coming out with like get started on PA5 video, I think, hopefully. So this is an old slide made by Sophia, AJ, and someone else. So thank them for the slides. We are not covering skip lists. We have seen enough skip lists. We are done with this. Yes, we are not covering this. Yeah. So today we're going to be looking at unordered maps and hashing. So the motivation behind unordered maps, hash maps, or sometimes they get, called dictionaries, and depending on the language, you're going to see these a lot. The motivation here is we can exchange space complexity for time complexity and vice versa. So if we say we're willing to use a lot of extra space to store our data, then the advantage of that is having more space, you can find things a lot faster. So whereas in vectors, everything has to be stored in contiguous memory, and then searching through that contiguous memory takes you a long amount of time. If you have a really big vector, then you can have a hashing function, which is what we're going to learn today, that maps elements that would have been in your vector across this larger space. And then by following the hash function, essentially in constant time, you can perform lookup. So I was hoping, okay, maybe the information is on this slide. So as you can see, the pros of a hash map is that you're going to have insert, delete, and search all take O of one time. And this is a big improvement over the vector. This is a big improvement over the linked list, over the tree. And it's really, really useful. So if y'all have ever touched LeetCode or tried to do like an actual programming project yourself, I don't think, honestly, I don't think I've ever used a programming like project personally for my personal projects that didn't use a hash map. So y'all, this is one to pay attention to. It's not like the skip list. This is going to come up over and over again. The cons are you did make a sacrifice, so you're going to have to use a lot more memory. As you can see in this example right here, this unordered map that we have on the slide, we've got a size of 11, so there's 11 possible elements. But because it's a hash map, we need to have a lot of extra space. And as you can see, we're wasting about half of it. Depending on the hashing method that you use and certain peculiarities of whatever your specific needs are, you might have more or less extra space, but nonetheless, you are less space efficient, more time efficient. And the other con is that ideally you would have a hashing function that maps to all of the boxes in this large space equally, right? So the perfect hash function is indiscriminate of input and is going to randomly proportion everything into 11 categories in this case. That's not always feasible, and in times where the hash function maps two different inputs to the same output, that's called a collision, and you have to address that. So today we're going to be talking about what that hash function looks like and how we deal with those collisions. So here's a little example right here. So we've got, looks like we are trying to use a hash map to represent a dog. And so the dog is going to have some certain characteristics. It's going to have a name, a color, and an age. And a good hash function is going to take these things and then randomly assign them to hopefully different places in the list, right? So we're going to insert the dog's name, the dog's color, and the dog's age as these things respectively. And then, so as you can see, we insert Fido gets hashed to 7, purple gets hashed to 9. And then we have a problem here because age ends up also getting hashed to 9. So now we are trying to put two elements in the same position, which doesn't work. So that's a collision. And so how do you resolve a collision? Well, there's a few different techniques. The most obvious and intuitive one, which is PA5 style, is to say, why can't I just put two things in the same bucket? And in which case you actually do put two things in the same bucket. And that's called the chaining method. So imagine that this array right here was really just a collection of head nodes and linked lists. So instead of having 11 elements in this array, imagine you had 11 pointers, and those pointers, led to linked lists, which in this case would be vertical. In that case, you could just say, well, I'm going to add to the list that is now going in this vertical direction. So that's one possible solution. That's kind of like the naive solution. A more in-depth kind of mathematical approach that doesn't actually take extra space, it's called linear probing. So essentially, in the example before, if we tried to put age at index 9 and there's something there already, we say, okay, well, we're just going to increase the index by 1 until we find a good place to put it. So as you can see, age would be mapped to 9. There's something at 9. We would add 1 to the index and we would place it at 10 because 10 is empty. So that's linear probing. There's quadratic probing. So imagine we were here, we would add 1, and then we would add 2, and then 4 and 9, and so on and so forth to avoid collisions. We're going to talk about that later. And then also there's double hashing. So instead of just using one hash function, we can use two hash functions. And the advantage of this is that if one hash function is pretty random and distributes things pretty evenly, two hash functions will be even more random and will distribute things even more randomly. So this is kind of like the high level overview. I'm actually gonna like do some examples so that y'all can see what this looks like. So if I went way too fast, no, I didn't. This is just to give you the idea. We already talked about chaining method. Okay, so if you're lost, you're probably in good company. I'm about to do an example. Anyone have any questions so far, like high level stuff? Bird's eye view. Any questions? Okay, so if nobody has questions, I'm gonna go ahead and I'm gonna switch to my iPad. Okay, cool. Can someone confirm that they can see this?
Yeah, I can see it.
Okay, thank you, thank you. So I believe we have our PT with us. So I can't see comments right now because I'm on my iPad. But our PT, she can see your comments. So if you need to stop me, unmute yourself. If you don't want to unmute yourself, PT would be happy to help. So from the slide before, I believe we had some series of input that looks something like this. And we were asked to build a hash map out of this. So the most important thing about a hash map, hence the name, is the actual hashing function. So let's go ahead and formalize what that is. So let's say in this case, we've got an array. I think from the slide it had 11 elements. So we're going to just say that hash of k, and k stands for key. So this is like hash of some key. And then we're going to define that function to be k modulus m, where in this case m is the size of the array that we were looking at. So m is array size. So I think in the example that we had on the slides, m was equal to 11. So let me just draw this real quick. So we got 1, 2. We had something that looked like this, and indexes 0 through 10, I believe. And so specifically, in our case, our hashing function is going to look like this. It's going to look like h of k is equal to k modulus 11, because 11 is the, because 11 is the size of the array. So essentially, if we try to if k is for some reason bigger than 11, the modulus function will handle that and will wrap around. That way, everything will always be mapped between somewhere 0 and 10. And that's one property of modulus, is that something modulus a number, in this case m or 11, the range of acceptable values as output from this function is in fact 0 to 10. So happens to work quite nicely with what we need. So let's go ahead and do these one at a time. So first we're going to call hash on 2. So h of 2 in this case is going to be 2 mod 11, and this is just 2. So first let's do let's do the chaining method first. So PA5 style, you're going to be doing something that looks like this. So I'm gonna just say up here, this is chaining method. And we're gonna redo this example for the other methods too. This is the chaining method, PA5 style. So we computed the hash value of 2. It put us at this index, and then we added to the linked list, which is at that index. I think pretty straightforward so far. Now we're going to do a hash of 8, and that's going to be 8 mod 11, and that'll be 8. So again, PA5 style, we're looking at this. So far, so good. Let's do hash of 11, and that's going to be 11 mod 11, and that'll be 0. So note, like I said before, something mod 11 will never give you 11. Like the highest you can get is 10. So 11 will wrap back around to 0. Hash of 13 is going to be 13 mod 11, and this is going to be 2. So this is our first collision, because we already have something at 2, right? But in the chaining method, that's why I did this first, because I think it's the easiest. That's really no big deal, because now we just add it to the same bucket. No big deal. Now we're going to add 10. So hash 10 is going to equal 10 mod 11. In this case is 10. So that'll go here. Actually, let me move this and redraw this. So that'll go here. And then I think we had one more, which was 19. So hashing 19 is going to give you 19 modulus 11, just 8, I believe. Okay, yeah. And so same thing as before. We just handle this collision by using the simple chaining method. So 19. And just like that, we have created a hash map. I think this is pretty straightforward. And like I said before in the high level overview, as you can see, we've got a lot of empty space. So this whole region here is completely unused. That being one of the cons, and then also we do have collisions. So these do come up. But if we wanted to search for elements, so imagine we wanted to search for 13, we could do this relatively quickly. So just as a review, if you had a vector and you know that 13 is somewhere in this vector, you're going to have to search through, the worst case, the whole thing to find your element, right? But because we have a function, which in this case is h, that maps elements to the position in their array, we know exactly where we're going to find 13, because we can just call this function. So hash of 13 is 13 mod 11, and then immediately we know if we're looking for 13, we find it at bucket 2, and then we traverse bucket 2 until we find it. So this is O of 1 time. Specifically, there is a little bit of a sticky case. Worst case here is obviously like the chaining method. What if you just keep putting things in a chain? Is this still O of 1? And I think we'll talk about that in future reviews. But for now, hash maps are O of 1. This is the chaining method. I think pretty strong starting point. So I'm going to rewrite these numbers. So we had what? 2, 8, 11, 13, 10, 19, I think. So these are our inputs. Okay, so now let's build a hash map using linear probing. Linear probing. Okay, so now we actually need 2 formal definitions to make this happen. So we've got the one that we had before, and I'm going to call this h1. So h1 of k is going to be equal to k mod m, or in this case, let's just stick to an array of size 11. So let's just say that it's k mod 11, and then we're going to have a second function. And the second function, I'm also going to call it h, but it's going to take a second parameter. So instead of just having the key, it's going to have k and then also I. And so like before, this is, hash some key. And then I here is going to stand for like how many times have you found collisions? So how many collisions? And intuitively, before I actually say what this is, what this means is that first, when we try to insert an element, we're going to insert the key, and we haven't seen any collisions. And if this runs into a collision, then we're going to try again. And we're going to have hash of key. We've seen one collision, and we're going to try again. So imagine we get another collision. We're going to try again. So now we've seen two collisions, and then imagine there's nothing there. So this is sick. That's, oh man, I suck at spelling. So if we get a successful insert, then we're good. And so the idea here is, how do we make it such that the number of collisions that we've seen before has some kind of meaningful impact on the position in the array in which we're putting the element, right? So with that in mind, let's go ahead and define, let's define our function to be similar to what it was before. So let's say it's h1 of k plus I, right? So this handles the linear probing in kind of a naive way. So this is like saying, if we've got our hash map here, and I think let's stick with 11 elements still. So 1, 2, 3. So I'm just gonna write this out one more time. Forgive me. So yeah, so this handles the same problem, same collision problem. So imagine we've got element x here, and then you know, hash of element y equals 4, and we're trying to put y here. We would handle that in this case by saying, okay, well, so if hash of y0 is equal to 4, and 4 is taken, now we're just going to compute hash of y1, and that's going to equal 4 plus 1, and that'll put us here. So that essentially, in a nutshell, is how we're solving this problem. Let's go ahead and see what this looks like with real examples. So first we've got h of 2, 0. So I'm just going to work over here again. So h of 2, 0 is going to equal h1 of 2 plus 0. And that's 2 mod 11 plus 0, and that's 2. So no problems yet. Now let's insert 8. So hash of 8, 0 is same idea as before. 0, and we can tell that this is 8, hopefully, right? Because 8 mod 11 plus 0 is 8. See, and then 11, see, so h of 11, 0, it's going to be 11 mod 11 plus 0, so this is also 0. So no collisions thus far. Let's add 13 and see what happens. I think I remember that this was a collision. So h of 13, 0 is going to equal, we're going to use our first hashing function, and then we're going to add I, which in this case is 0. So that's 13 mod 11 plus 0, which is 2. And this is a collision. So now we've got to try again. So we're going to compute h of 13 with one collision, and that's going to be, these two values are the same. So this value stays the same each time, but now we are adding the number of collisions. So in this case, that is going to be, we decided 13 mod 11 was 2 plus 1, and this is 3. As you can see, 3 is empty, and 13 will go here. So collision avoided. So we're going to add 10. I can just add it there. I don't actually want to worry about that. Now let's look at adding 19. So 19, so h of 19, 0. It's going to be h1 of 19 plus 0. So this is 19 mod 11, which is 8. And I think we already had something at 8. So I'm going to have to go for one more iteration. So this is h1 of 19 plus 1, 8 plus 1 is 9, and we put it here. So this is linear probing, and as you can see, as opposed to the chaining method uses a lot of extra space, right? So all this space that we had, here in the middle, not only does this not get used, but we are also using extra space here. So chaining method, very space inefficient. It handles collisions in kind of a naive way, Whereas for the linear probing method, as we can see, this is a little bit more elegant because we still have this empty space, but there's less of it. And the space that we do use was part of the array, right? Like we're not branching out into this new dimension. The problem, well, actually, I can think of two problems with the linear probing method that we haven't addressed. Is number one, the way I wrote this function doesn't handle a wraparound, right? So imagine we're trying to add the value 8 right here to our list now. And so something is already n8. So we would linear probe to the next entry, and there's something there, and there's something there. And then our function is going to tell you to keep going. So this is technically wrong because this will technically go out of bounds. So really, our linear probing function should look like this to handle the wraparound just in case. So I didn't want to bring that up at the beginning because, that's kind of an edge case and it's potentially confusing, but that's one possible issue that I can see. And then the other possible issue that I see is that you might have to probe for a really long time to find where you need to insert your next thing, right? So imagine you are inserting, for instance, like something that would go into this element here, right? So imagine you were inserting, I guess, in this case, you're trying to insert, what's something mod 11 that gives you 8? So can someone think of a good number that would give us a problem, like off the top of their head? I'm trying to think. Maybe 30 would be. Yeah, so 30. So 30 mod 11 is going to give us 8, right? And so if we try to put 30 there, it's not going to work. So we're going to probe to the next entry, and then that's not going to work. And then we're going to probe to this entry, and that's not going to work either. And then we're going to probe here, and also no dice. And then finally, we would find our place where we put our element. But then if we did that again, right? So if we try to insert 31, we're going to have to probe here, 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 here. And it's no good, right? Potentially, you're doing, M probes per insert. So this is taking what should be an O of 1 algorithm and is making it significantly worse. So chaining method kind of has some downsides because you're kind of wasting some space, and potentially you might accidentally put everything in the same linked list. And then the linear probing method is a little bit better, but we still have this issue of you might have a bunch of things probed linearly right in a row, and this is known as a cluster. So this is a cluster. And we want a hashing function that avoids these things. So that being said, let's redraw our input. So I think our input, I think it was this, if memory serves. So now that we did this, and I don't think I'm going to cover quadratic probing. Quadratic probing would literally just be this. Right, so not a huge difference. I don't think that difference is meaningful enough for me to cover it. If you like, let me just say as a side note to anybody who's here, if you are interested in like cryptography or cryptocurrency, if you like Bitcoin or I don't know, cybersecurity, any of these topics, you can go really, really deep into hashing. In fact, A&M offers a math course called Math 470, and I haven't taken it personally, but I know people who've taken it, and it's really interesting stuff. I mean, this rabbit hole goes as deep as you want it to go. So if you're looking at this kind of stuff and you think this is super interesting, please go deeper down the rabbit hole. But for today, we're gonna skip quadratic probing. I don't think it's meaningful enough to cover. So the last thing we're going to look at today is double hashing. This kind of addresses some of the issues that I brought up previously. So we've got double hashing. Okay, double hashing, yeah. So the issues that I mentioned previously were with functions that are not randomly mapping to the space, right? Ideally, if we have some kind of array and some kind of hash function, ideally we want a hash function that is going to be randomly putting things in this array, as evenly and as non-discriminately as possible. That is ideal. And so double hashing accomplishes this by leveraging the randomness of two different functions. So our first function, and we're going to have two, is going to look very similar to what we saw before. And this is going to be, once again, k mod m. In this case, the size of the array is 11, so we can just write that here. And the second function, the second function is going to be k mod a different number. So it's going to be this. Let me redraw that k. It's nasty. Okay, yeah. So now we've got two hashing functions. And as let me be consistent. Yeah, if I'm gonna try mod like, okay, yeah. So now we've got two hashing functions. Hashing function 1 and hashing function 2. They look kind of similar, but maybe a little bit different. Oh, oops. I'm so sorry, y'all. If y'all are like taking notes and writing with pen, I actually owe you an apology. It's terrible. Okay, anyways, where were we? So this kind of looks similar to hashing function 1, right? Except now we've got this extra term out here and we're subtracting what used to be something similar to hashing function 1. So what's going on here? Like what's up with this? So the idea behind this hashing function is that any huge number, mod 11, is going to hopefully theoretically randomly map somewhere between 0 and 11. And then likewise, any huge number k is going to hopefully randomly map with a 1 out of 7 probability to a space of 0 through 0. I said 0 through 11. It would be 0 through 10, and then this one would be 0 through 6. So potentially with our second hashing function, we're looking at a search space that is potentially 7 minus 0. It's potentially 7 minus 1, all the way through potentially 7 minus 6. So the output of hash 2 could potentially be 7, could potentially be 6, all the way through 1. The reason that we write it this way is because we want to guarantee that the second hashing function is fundamentally always non-zero, right? So the output here, output is greater than 0 for all k. Oh, oops. I'm sorry. Okay, so output is greater than 0 for all k, and that's important. And I think this course is what I just drew on the left. This course is going to write the second hashing function like this. I think you could also do this. I think k mod set, and this would kind of give you the same result, right? Because this guarantees that it's always non-zero, and then potentially it could be all the way up to 7, but don't worry about this. All you need to understand intuitively is that the first hashing function hopefully gives you some random number, and the second hashing function hopefully gives you some random number, and then the two of them together is going to do a better job at avoiding collisions. So like we did before, let's go ahead and draw our array. Just like this. So 1, 2, 3, 4. And let's go ahead and label the indices of this array. Okay. So we got this. There's one more missing piece that we need before we can just jump into actually working this problem, which is how do we stitch these two together, right? So let me go ahead and formalize that. So we need to say what happens when we run into collisions like before. So remember, k is still the key, and then I is the number of collisions that you've seen. And for our cases now, let's just say h of ki is going to equal h1 of k plus h2 of k. And this, for our purposes right now, is going to be a suitable combination. Let's just see what happens. So let's start with inserting, I think, 2, right? Yeah, so we're going to hash 2, seeing 0 collisions, and that is going to be equal to applying the first hashing function and then also applying the second hashing function. And so that's going to be, let's just go ahead and evaluate this. So this is 2 mod 11 plus 0 times 7 minus 2 mod 7. We don't even have to evaluate this because we know it's going to 0, and thus we put our first element 2. Kind of not super exciting, kind of a little anticlimactic, but let's keep going. So h of 8. So I think we're going to see the same thing here. So we're going to apply 8 to both of our hashing functions. And we know right away this is going to be 0 because we haven't seen any collisions yet. So if this comes up on a test, and it will come up on a test, it's a good rule of thumb to know that this second term, the second term of this hashing function is always going to be 0 until you reach a collision. So you don't need to worry about computing the second hashing function until after you found a collision and you're resolving it. So this is going to give us 8 mod 11. That's going to be 8. So again, a little anticlimactic so far. Let's add 11, and I think we're going to see the same thing again. So bear with me. Plus h2 of 11. We know this is 0, and we're going to get 11 mod 11, and this is 0, so 11 goes here. All good so far. Let's add 13. And so this one in the past has given us a collision, so let's see what happens here. So this is going to be the first function plus the second function. And that's going to give us 13 mod 11. And this is 2. And as we look, I think something is already here. So we can't use the spot. So now we've got to try again. And now that our I term is non-zero, this is no longer trivial. So this term is actually going to affect our hashing function now. So we've got h1 of 13, and we know that this is 2. But this time we're going to add h2 of 13 and actually compute it this time, which is going to evaluate to 1 times 7 minus 13 mod 7. And I think 13 mod 7 is 6. So I think it's this. So I think it's that. So I think we're putting it back at index 3 because it's 2 plus 1, I think. Yeah. And by the way, y'all, if I make like a stupid algebra mistake here, like, it's definitely possible. Hopefully I've at least stuck you with the actual concept. So don't be tripping. And there is a mistake on the slides, by the way. So if you go back and you look at the slides that I was sharing at the beginning of this review, and you go through the string of numbers on that slide and you follow the hashing function, it is actually mistaken. Like, they do actually put things in the wrong place. So don't trip. It is very easy to mess this stuff up. Even the TAs do it, myself included. Okay, so we added 13. Let's add 10. So 10 is going to be this. So 10, 0. It's h2 of 10. And you know this is 0. So 10 mod 11. Okay, so that will go here. And then, so here's the interesting one. 19 is actually quite interesting in this example. So we're going to start by computing the initial hash. And we can assume that we don't need this second hashing function yet. And so this is going to be 19 mod 11, which is going to be 8. And as we can see, something is already there. So now we get to resolve this collision. So let's try h of 19 with 1 collision, and this is going to give us h1 of 19, which we already know this is 8 plus h2 of h2 of 19. Oh man, I was doing this in my head. Oh wow. My bad, y'all. Okay, so if anyone was confused where I got the 1 from previously, I forgot to put that here. So The second hashing function is actually, you're going to have your number of collisions times the second hashing function. So you either formalize it like this, or I think it would make more sense to handle it like this. So let's do this. Okay, yeah. So sorry if y'all are trying to follow along and writing in pen. I actually do owe you an apology because I did that implicitly here. Right at first it was 0, which is I times H2, and then it was 1 times H2. So the double hashing is very similar to the linear probing in the sense that the number of collisions is also an important term. So sorry if I forgot to make that point. Okay, anyways, where were we? So now I is 1, so we're going to do 1 times H2. It's going to be 1 times, let's see, 19, no, it was 7 minus 19 mod 7. And I think, oh, and let me be consistent. I think 19 mod 7 is 5, right? So 7 minus 5, so it's 1 times 2. So it's 8 plus 2. Okay, so now we're going to try to put 19 at index 10. You can see there's already something there. So now we're going to have to repeat the process one more time. So h of 19, and now we found 2 collisions. It's going to be h1 of 19 again. And we already know this is 8. This one doesn't change. Plus 2 times h2 of 19. And we know that h2 of 19 is 2, because we evaluated it in the previous step. So this is going to be 2 times 2, which is 4. So we got 8 plus 4, and that's going to be 12. Okay, and so we have encountered the same problem that we had with linear probing, is that we didn't specify that our function has got to wrap around. So let me make yet again another addition to our double probing formula, and I promise this will be the last one actually. So now we have accounted for what happens if the input gets bigger than the size of the array. We just wrap back around, which in this case is going to give us 1, I think, right? 12 mod 11 is 1. So can we put 19 at index 1? Can we do that? Yes, we can. Aha. Okay, let me actually draw that in a way that is not terrible. Okay, so that's double hashing. It's kind of a lot to handle. This formula is, non-trivial. It's kind of a lot to look at. I think I explained it piece by piece, hopefully, so that conceptually you know what's going on here. Let me actually walk backwards through an example, see if that'll help explain it too. So let me rewrite our formula. So our formula was this. So h1 of k is going to be k mod m, and then h2 of k is just some different hashing function, k mod 7, and then we're going to say that putting it all together is going to look like this. So we've got the first hash plus the number of collisions times the second hash. And then we need to wrap this in another modulus just in case the output gets too big. So this is the double hashing formula that we're working with. Let's go ahead and search. So let's search for 19 and see what happens. So we're going to search by essentially just walking backwards, and this is going to give you before we do this, let's actually compute our hash function. So h1 of 19 is 19 mod 11, and that's 8. And then h2 of 19 is going to be 7 minus 19 mod 7, which is 2. Okay, so we're first going to look at 19, 0, and that's going to give us 8 plus 0 times 2, So we're going to search at index 8. You can see we search at index 8. 19 is not there, so we have to keep searching. And now we're going to search at 19.1. And so that's going to be this. So we're going to look at index 10. And index 10, something is there, and it's not 19, so we have to keep searching. And let's see, so h of 19.2 is going to give us 8 plus this. But remember, we wrapped it in the modulo just in case we have to wrap around. So now let's search at index 1, and then we found it. Okay. So that's what I have for hashing. Sorry it took me so long to actually write this formula in its totality. But essentially one hashing function, a second hashing function, they're different. It's important that the second one is always non-zero. You multiply the second one by the number of collisions you've seen, and then you have to add this wrapper again, just to make sure that you're not going out of bounds. And as a recap of what we've seen so far, let me see. So we first looked at the chaining method, which is kind of the naive approach to the hashing problem. We defined the hashing function as hash of some key is equal to key modulo the size of the array. And as you can see, that maps every possible input to an output space that is the size of our array. And we can handle collisions by just creating linked lists. And huge hint, this is PA5. This is exactly what you're doing for PA5. We can instead decide to handle collisions by incorporating the number of collisions that we've seen as a term in the equation. So in this case, we've represented it as I. And then that can be just a number that you add. And that number essentially gives you linear probing. We have to add this modulo m wrapper at the end to make sure that our answer stays in bounds. And that handles collisions with less space, but it causes clusters, which is not ideal. And then double hashing essentially accomplishes the same thing, but it has a less chance of developing clusters. So it is a better algorithm. And then here we rewrote the formula. So the whole formula is, where is it? Whole formula is this. And the search formula is literally you just take the hashing formula and kind of just walk backwards until you find what you're looking for. And in this case, we did end up finding what we're looking for. So that's kind of a summary of what we did today. This will be on tests and quizzes, so I do think y'all need to know it. I guess one more thing that I wish I had mentioned earlier is that when we picked m here, like this term, it's important that m is a prime number, because that also helps reduce clustering. I should have mentioned that earlier. Kind of the motivation behind that is like when you do have to wrap around, if you're wrapping and dividing by a prime number, it's less likely that you're going to be putting elements in the same place. So again, cryptography is a massive rabbit hole. You need to know at least this much for this class. I encourage you to go learn more if you're interested. And yeah, so that's hashing. And so while that was a rather technical Sunday review, it is good to understand this stuff very thoroughly, because hash maps are like, maybe if vectors are the most useful data structure, hash maps are a very close number two. You will be seeing these when it comes to like any type of programming, pretty much. So it's good to know what's going on under the hood. And yeah, that's about all I had. Anyone have any questions? Anything not clear? Okay, well, hopefully I didn't scare you off. I think hashing is cool. Uh, yeah, someone says thank you. Yes, thank you for being here. If y'all are still here after test two, y'all are so close. Y'all are so close to the finish line for this class. Stick with it. I guess back to the grind on Monday. Uh, I hope all of y'all get wonderful scores on test two. Hope all of y'all get to work on PA5 and that it goes well. Other than that, y'all enjoy your weekend. Good to see y'all.
Actually, a quick question.
Yes.
So when we're starting to work on PA5, like how do you recommend starting it? Like should we be like drawing out stuff and like
Yes.
thinking it through first?
Yes. Yes. So I have you looked at the GitHub? Because the GitHub is a little bit daunting, I'm not gonna lie. I'm thinking I should release a video or kind of like walk you like step by step, like you want to do these functions first and then these functions and then draw actual pictures. So hopefully I'll have that out by Monday. But yes, I encourage you to draw out these things 100% because there's a lot of like interlocking function calls for PA5. So
Yeah.
uncontrolled complexity will get to you. So yes, yes, pen and paper for sure.
Okay.
Yeah, so
Thank you.
like when I did this, they had a lot of helper functions, and I would recommend that you do those first.
Should I find the helper functions probably at the bottom of the code?
Uh, I
Is it
look.
I
like how
think
clone is at the bottom for the
I think
previous
they
one?
all have underscores
Oh, okay.
in the names. Yeah.
Yeah,
So
it's
do
it's
the ones with
something
the
like that.
underscores
Yeah.
first.
Okay. Thank you.
Mhm.